Week 5 of our course and chapter 10 of the book concerns itself with the properties of gases. Gases are very low in density. They have low mass. They have low interparticle attraction, which means that most of our gases are going to be non-polar. That's covered in a later chapter in the book, but it's good to know now. They're compressible, which is a consequence of them having low density. We're going to talk about this diagram here in a minute. And they occupy the entirety of the volume of the vessel that they are put into. And the measurable thing about gases is that they exert pressure. Okay, so here's what we know. Solids, liquids, and gases. If this is the solid, liquid, and gas phase of the same material, so the particle size is the same, solids, those particles pack together very, very closely. So I get a lot of mass in this volume. Mass per volume is density. Solids have high density. Liquids spread out a little bit, and we know how to turn solids into liquids. We heat them up. So the thermal energy separates the particles a little bit, gives them some motion. I have some separation between the particles. I have less mass in the same volume. I have lower density. By the time we get to be a gas, there is almost no mass at all in this volume, and the interparticle distance is much, much larger than the size of the particles themselves. That's a real point of recognition for gases. The distance between the gases is much, much larger than the size of the gas themselves. This gives them low density and allows them to be compressed, because you can squeeze the particles into that space, knowing that they're only going to become a liquid when the particles are this close together. Gases exert pressure, and pressure, well, there are lots of different ways of measuring it, lots of different units. Pressure is force per unit area. So something like on the tires of your car is measured in pounds per square inch. That is a force per area, but we can't use pounds per square inch because it's not metric. The actual SI, Standard Institute's unit of pressure in science, is supposed to be the Pascal. But I'm going to show you at the bottom of the page, the Pascal is a terrible number, and so we don't actually use the recommended value. Bar is a measure of pressure. You might have heard the meteorologist on television talk about bars and millibars of atmospheric pressure. Torr is a measure of pressure that comes from a barometer, and barometers measure atmospheric pressure, that is also translated as millimeters of mercury. And then we finally get to the unit that we're going to use. And the unit that we're going to use is the atmosphere. And the atmosphere very, very simply says that the amount of pressure that I'm experiencing right now from the atmosphere is 1. So every single day, with small variations depending on what the weather is doing outside, our atmospheric pressure is 1 atmosphere. And 1 atmosphere turns out to be worth 760 torr, that's the same as 760 millimeters of mercury, or 101,325 pascals. That's why we don't use the Pascal. Which turns out to be equal to 1.01325 bar, because a bar is 10 to the 5 pascals. We're going to stick with the atmosphere. Pressure arises when the gas particles bounce off the inner walls of their container. So pressure is going to be related to a number of variables that we might be able to change and observe. Pressure, first and foremost, is going to be related to the energy at which the gas particle is going to bounce. Well, energy, kinetic energy, the energy of motion, you might remember from high school physics, is half mv squared. So there are two components in there. One of them is velocity. Velocity is speed in a given direction, and that speed is going to be directly related to temperature. As you increase temperature, you increase thermal energy, which is kinetic energy. You make the particles move faster. And if the particles are moving faster, then they hit the walls of the container with more force. The other thing that's embedded in the energy equation is mass. So two particles having the same energy, if one is heavier than the other, if they have the same energy, then the heavier particle is traveling at a slower speed. But if I've got a heavy particle traveling at a high speed, then my impact is going to be very strong indeed. The other thing to take into account is N, the number of moles. If I just have the single particle bouncing around in the box, then it alone is responsible for all of the pressure. If I add some additional gas particles into the box, then they also contribute to the pressure. So the pressure inside a container that has more gas molecules in it will be higher than when there are less gas moles inside it. And then that brings us to volume. If I shrink the volume of the container down to something smaller, then the particles travel less time from wall to wall. It means that the time between collisions is shorter. So I get more collisions per second. More collisions per second means higher pressure. So pressure is directly related to energy, directly related to temperature, directly related to the number of particles or moles, but inversely proportional to volume. The kinetic molecular theory of gases models the population of a gas this way. It's going to say that we've got thousands, maybe hundreds of millions of gas particles inside even the smallest sample. Now, not every single one of those gas particles is going to have exactly the same speed. There's going to be a distribution of speed, and it follows this trend. So if I were to plot amount versus speed, I would find that here's my average. This is the average speed of my gas molecules. But some of my gas molecules are going to be what we would call highly energetic. And it turns out that this small population of gas particles that have picked up more heat than the regular population of gases, these guys right here, they're responsible for a lot of the pressure that is measured. Now, something interesting happens when we take a population of gas like this and we heat it up. When a gas is warmed, the shape of the curve shifts to the right, to higher speed. So the average speed when the particles were cold is here, and I've moved to a higher average. But that's not the important thing. The important thing is, at some point we had said that molecules right here were very high in energy, and it was those high energy particles that contributed disproportionately to the pressure inside the container. Well, now I have lots more high pressure particles. And it's this that contributes, as well as that, but this is largely responsible for the increase in pressure when a gas particle gets hot. So those fundamental findings bring us to these simple gas laws. Boyle's law says that the pressure of a gas is inversely proportional to its volume. This little alpha symbol is the proportionality sign. It's not the same as an equal sign because there is another number in here somewhere. There's a constant somewhere associated with that. So it's the same as saying pressure is equal to a constant divided by volume, which means that pressure times volume is a constant. Well, if pressure times volume is a constant, then the pressure times the volume at the start of anything that I do has to be equal to the pressure and the volume at the end of whatever I do. So if I take a balloon and I blow it up, I know its pressure and its volume. If I let some air out of that balloon and I now know its new volume, I automatically know its new pressure. So Boyle's law can be written as P1V1 equals P2V2. Charles's law relates that the volume of a gas is directly proportional to temperature. And that temperature is going to be in Kelvin. Remember, we don't use the Celsius scale for calculations because the Celsius scale could go negative. You can have negative numbers in the Celsius scale, which would mean that at some point, that number for volume could go negative, which is impossible. Volume cannot be negative because volume is a three-dimensional space. So volume is directly proportional to temperature, which means that volume divided by temperature is a constant. The volume divided by the temperature at the start of whatever I do has to be equal to the volume divided by the temperature at the end of whatever I do. So if I have a balloon and it's at room temperature and I change the temperature by putting this balloon in the refrigerator or taking it outside on a hot day, I can figure out what the new volume of that gas is going to be. Avogadro. Avogadro is a name that is associated with the number of moles. And Avogadro tells us that the volume of a gas is directly proportional to its number of moles. So if I were to do some kind of manipulation where I change the number of moles in a container by letting some of the gas out of a balloon, I would be able to know what the missing number is, because V1 over N1 equals V2 over N2. Avogadro further tells us, and this is important because remember, the distance between gas particles is immense in comparison to what the size of the gas is. That means that all gases behave fundamentally the same way, and that 1 mole of any gas at all, occupies 22.4 litres at something called standard temperature and pressure, which is 1 atmosphere and 0 degrees Celsius, but again, we won't be measuring that in Celsius. That would be 273 Kelvin. So, standard temperatures and pressures, STP, is equal to 1 atmosphere and 0 degrees Celsius, or 273 Kelvin. Now, those individual gas laws, Boyle's law and Charles's law, they can coalesce, and they coalesce into something called the ideal gas law, which is PV equals nRT. P has to be written in atmospheres. V must be written in liters. And the reason for that is that this number in the calculation, R, is 0.0821. R is the universal gas constant, and its units are liter atmospheres per mole per Kelvin. So if you were to put a number here for temperature into this calculation using Celsius, you'd get the wrong number. It must be in Kelvin. If you were to use anything other than moles here, you would use the wrong number. You would get the wrong answer. If you used milliliters or fluid ounces or any other kind of volume here, it would not match with the universal gas constant, liter atmospheres per mole per Kelvin. Atmospheres, liters, moles, Kelvin, they all have to match the units that are included in the constant. So when it gets time for us to do a calculation for an ideal gas, part of the trick is to take the information that is given to you in the question and translate it into a form that is accessible by this equation. Make the units match. An ideal gas is just a gas that obeys the laws. If it obeys the laws properly, we call it an ideal gas. If it deviates from ideality, we call those gases real gases. Some of the assumptions that we make about ideal gases are that when two particles pass each other, there is no interaction between those particles, so they don't deviate the path of the other particle around it. There's no attraction or repulsive force between particles. And that the size of the particle itself is negligible in terms of what the distance between the particles is, so that we don't have to worry about them having any intrinsic volume. Those two things are not true. And as we get to higher pressure and lower temperature, getting closer to being a liquid, if you pressurize a gas, eventually it will liquefy. If you take a gas and you remove heat from it, eventually it will become a liquid. So if I set up conditions where I am close to the liquid boundary, my ideal gas now starts to behave like a real gas. And we're going to take the ideal gas equation, PV equals nRT, and make two adjustments to it. One is to show that the particles do have some attraction or repulsion to each other, and the other one is that the gas particles themselves do have a volume. This is called the van der Waals equation. Again, because the gap between gas particles is much, much larger than the size of the particles themselves, gases act independently. So if I have a mixture of gases, each of the particles of each of the components in that mixture acts as an individual. It has its own pressure. Dalton's law of partial pressures tells us that the total pressure exerted by a mixture of gases is equal to the sum of all the component partial pressures of those individual gases. So here's a little container, and it contains some A and some B and some C in different amounts. The total pressure inside that container is equal to the pressure exerted by A plus the pressure exerted by B and the pressure exerted by C. All of these added together or summed. And because the pressure of A is only a component of the total, it's called a partial pressure. Diffusion is the movement of particles away from an area in which they are at high concentration into an area at which they're in lower concentration. And effusion is the same as diffusion, except that it has to go through a hole or through a tube. Causing diffusion to happen through a tube or a hole allows us to measure the difference from one side to the other of an experiment. And this has allowed us to get to Graham's law of effusion, which states that the rate of effusion for two gases, one divided by the other, is equal to the square root of their formula masses. Now, our book states Graham's law of effusion this way in terms of rate, that rate 1 divided by rate 2 is equal to the root of the formula mass of 2 divided by the formula mass of 1. But remember, we said right at the beginning of this course that a rate was a derived unit, and that a rate could be something like miles per hour or meters per second or dollars per day. It is something divided by time. So if Graham's law is ever described to you in terms of time, because rate and time are inversely proportional to each other, the time that it takes a gas to effuse through a hole in comparison to the time of a different gas to effuse through the same hole is now equal to the root of the formula masses of those gases in the correct form. So time 1 divided by time 2 equals root of formula mass divided by formula mass 2. 1 over 2, 1 over 2. If it's in terms of rate, because rate is the inverse of time, 1 over 2 in terms of rate gives you formula mass 2 over 1. Again, rate 1 divided by rate 2 is the root of mass 2 divided by mass 1. Time 1 divided by time 2 is the root of mass 1 divided by mass 2. That's Graham's law of effusion.